Hello and welcome. My name is Dr. Lena Weigold and I'm a product manager at RED. Later on, I will also have a slot, but now I have the pleasure to welcoming you to our webinar day on batteries. In the next 2.5 hours, we will going to listen to 5 interesting presentations from the Werder Scientific Company. So each brand has a slot of 30 minutes. And you are invited to attend every slot that is of interest for you. So with the provided link, it is possible to leave and to enter the webinar again. At the end of the presentation, at the end of the webinar day, we will provide a link with the presentation slides, so there is no need to take notes. But now I would like to give word to Dr. Jürgen Adolfs. He is the Director of the Product Management at Microtrack, and he's going to introduce the topic of today. Hi, Jürgen.
Hi, Lena.
Please tell us what are the biggest challenges of battery technology today, and what are the benefits of working together with Werder Scientific?
Yeah, well, let's see what and where batteries are used. Well, batteries are everywhere. As you see, the global electric vehicle battery market size is projected to reach about more than $80 billion within 2026. And mobility is also high impact for me, since I bought an e-bike just before COVID started. And so it was easy for me to explore the hilly area where I'm living. And meanwhile, the market for e-bikes, or the sold e-bikes, number of e-bikes, is much higher than normal e-bikes. Interesting enough. So, of course, we have batteries in our daily life, in our mobile phones or computer systems, but in the cars and everywhere. We use it for mobility, but we use it also for storage of energy we get from the solar panels, from wind energy, for example. Of course, batteries are also found in a lot of medical devices. So to make the implants of for hair, for heart, or whatever, smaller and smaller, and they need a battery. Interesting part is also robotic, because a robot without a battery will not work. And robots are meanwhile very effective. They can jump and run. It's an interesting field too. Well, let's see how a battery is built up. We use raw materials like graphite powder, electrofoils, and so on. And these are materials we also would like to investigate and to do some research with our equipment I will show, which will be shown later. So we do have the electrode manufacturing by slurry mixing, coating, drying. Then we have the process of calendering, pressing an electrode, then slit it and cut it. And finally, we assemble the cell. Mm-hmm. A picture shows here the lithium-ion battery in action. So we do have the cathode and an anode and the separator between both. The electrons are going from the anode to the cathode, and the current is going from the cathode to the anode. But we need also electrolyte. So these can be a liquid or even solids. We will see also later examples for this. Well, if you go now to the improvement of batteries, there are 2 main aspects. One is to cut down the battery costs and to improve performance. And also this covers safety, this covers life cycle and everything, and recyclability. Simply spoken, we can say we have to reduce the cost by factor 2 and increase the performance and all the other safety and performance issues by factor 2 or more. And this is to be done within the next few years until 2035. So we have not much time. And to help you to achieve this goal, we are offering solutions from the Werder Scientific division. And we are consisting of 5 business segments. One is the heat treatment by CARBOLITE GERO. elemental analysis by ELTRA. Materialography, hardness testing, polishing, and so on of metals is done by QATM. Milling, sieving, sort of by your company, Elena, by Reg. And particle characterization, porous materials characterization is the business of my part, of my company, Microtrack MRB. So at all, we are consisting of 10 manufacturing sites. We have 22 sales offices, a revenue of 250 million, and more than 1,000 employees. So the battery is, well, not only battery, we have a cycle. We have basic materials, we have components, we have the assembly, the final battery, and also recycling. For the basic materials, all of our companies are offering solutions. So for the metals, the graphite, polymers, and so on. For the components, mainly 3 companies, CARBOLITE GERO, Reg, and Microtrack MRB, is offering equipment that is dealing with electrode powders, anodes, cathodes, electrolytes, and separators. For the assembly, ELTRA and QATM are the companies you should contact. And finally, in the recycling, almost all of the companies again are involved. And so that closes the cycle for the battery life, from basic materials, components, assembly to the recycling.
So thank you very much for this appealing introduction and for making us to look forward to what is to come. Before I start with my presentation, I'm the first one who's going to present the company Reg. I would like to add one final general note to our audience. So if you have any question, please use the Q&A function of the webinar software. Our team of experts is online and they will be happy to answer your questions at any time. We will further discuss crucial questions after each session live. So please do not hesitate to ask. Okay, and then thank you very much, Jürgen, for the introduction. And let's start with my presentation from the Reg company. Let us take a closer look at Reg application-specific solutions. Reg is a leading provider of size reduction and particle sizing technology. It was founded more than 100 years ago in the year 1915, and it's known for their highly quality products. It's all about milling, sieving, and assisting. Today, I will show you how our devices are used in the field of battery technology. So I want to give you 3 examples for applications. The first is from the sector of basic materials, and it's about sample preparation. Here I will focus on jaw crushers. The second example is taken from the component sector, so the development of new and efficient materials. And for this, I will introduce the family of ball mills. And the third example is to show the applications of our products in the field of recycling, for example, in terms of quality control. So let's start with the first example, the sample preparation of copper ore. This is performed in the mining industry, and analysis is done to understand the mineralogical composition or the type of elements in this ore. Copper, you may know it, plays a crucial role for the cathode foils of a battery. So for the analysis, a representative sample is needed. Only then the analysis result will be correct and reproducible. To achieve this, most of the time only a few grams of material is needed. So you need fine particles, a homogeneous sample, which is also contamination free. For this, we have to grind, to homogenize, and to divide the sample. And this is how the process looks like. So you can see we have 2 steps here. The first is the pre-crushing step, and the second is a fine grinding step. For the pre-crushing, we use jaw crushers. So you can reduce particle size from 250 millimeter, for example, down to around 10 millimeters. And you can use, for example, BB600 or the BB50 jaw crusher. And this is how a jaw crusher is working. So the functional principle, you see you have two jaws. One is moving and the other one is fixed. And the material is inserted and crushed between these jaws. As soon as the material is small enough to pass the gap, it falls down in the receptacle. So for the second step, the fine grinding, you need to process a small part of your sample. And instead of just taking randomly a part of your sample, we recommend to use a sample divider, for example, PT300, an XL model, or the PT100. And then you proceed the second step, the fine grinding, for example, with the disc mill RS200. You can grind down to 63 micrometers for XRF analysis. And you can also use another device from our assisting portfolio to the pellet press PP35 to produce these tablets for XRF analysis. If you want to perform XRD analysis, you should use another device, the Macron mill, which is a very gentle grinding process to preserve the mineralogical composition. You can even grind down to 4 micrometers. So what is important to understand is this is the process to crush copper ore, but it's also the same machines if you have another hard and brittle material, let's say NMC material. So you're using the same machines, but of course you have to adapt the setup, the process parameters. In the case of copper ore, let's have a look at the details. We used the BB600, which was equipped with jaws made of manganese steel. So in terms of cross-contamination, you can also choose another material, for example, a steel for heavy metal-free grinding or cast iron. And here we used manganese steel and we choose a gap width of 25 millimeters. So in only 15 seconds, the material was crushed down to 14 millimeters. BB600 is a XL device, so it has a high feed size and a high motor power. It's optimized for high throughput, but you can see we have 8 other models of jaw crushers, which they have their own DNA or the spider graph, so different movement, different speed, different shape of jars, and you can choose the best device and the best setup for your application. Now let's have a look at the second example. So here I would like to talk about material development, a very common application of our mills. And we are talking about the manufacturing of electrode materials. As you know, this manufacturing process consists of several small steps. And for these also laboratory ball mills are used. For example, for the pulverization of precursors, for particle size reduction, powder mixing, particle coating or slurry mixing, for mechanochemical synthesis, breaking agglomerates, or sample preparation in case you want to do an analysis. So we offer basically 3 types of ball mills. They all have in common, all ball mills work with the same principle. You have a jar, you put in the balls and the material, you close the jar, and then you start shaking it to break the material. So these type of machines differ in terms of the movement of the jar. So a planetary ball mill follows this movement. That's where the name comes from. It looks like a planet that is surrounding the sun. A mixer mill has another movement pattern. So here you see that the jar is moved in a horizontal position like a shaking process, more like a shaking process. And the Emax has a very specific movement pattern, which is very efficient in terms of crushing materials. So let's have a look at a specific application example, the particle size reduction of silicon. So silicon is an alternative anode material, and the task was to do nano grinding, so achieve very small particles. So we have to perform a wet grinding process. This is possible with Emax, so MM500 Nano, in a 125 milliliter jar and very small balls at high speed and several hours. And this is a result. So it was possible to shift the particle size down to, in case of Emax, down to a finest D90 of 0.25 micrometers. And in case of MM500 Nano, there were 90% of the particles were smaller than 0.43 micrometers. So you see, we not only shifted the curve, but we also changed the shape of the curve with the specific device that was used. So this is, you can see there are different results from the machines. Another example is the particle size reduction of thiophosphate. It was performed in MM500 control, same size of jar, 5 millimeter balls. And the outstanding property of the MM500 control is that you can control the temperature during the grinding process. So you can cool or freeze the sample during the grinding process. And with the thiophosphate, it's a lithium sulfur material, which is used for solid state batteries. It's an electrolyte, a solid electrolyte. A particle size was achieved that is optimally, you can use it for dense packaging to improve the energy density of these type of materials. And I also want to mention mechanochemistry, which is also performed with ball mills. It's a field of research where you put two materials inside the jar, and by processing it, you induce a reaction and you receive a new product, a new material. This is used for developing new lithium-ion battery materials, but also for the recycling. And these processes generally require long process times, high energy input, temperature control and atmosphere control, and jars of small cavities. We are talking about research and small sample amounts, which sometimes are very expensive. So the wedge mills are suited for mechanochemistry, and not only because we also offer a wide range of accessories. So for example, adapter and 2 milliliter tubes, as well as multi-cavity jars for these small sample amounts. But we also have the aeration lids to control the atmosphere, and the grind control, which enables to measure the temperature and pressure development during the process. Finally, let's have a look at the third example taken out of the recycling stage. So you know that for recycling, many different steps are necessary. And also here, our mills and sieving machines are used, for example, for crushing, for sieving in terms of fragmentation, for sieving in terms of particle size characterization, and the mills are used for sample preparation for analysis. So this is a question of quality control. You want to control a recycling process to see how efficient it is, how much of the valuable metals is recovered in the black mass, how many of the valuable metals are remaining in the other fragments. So with the following slides, I only want to show you that we can prepare samples of different materials. So if we look at the housing parts with this polymeric, we can cut it with a cutting mill, SM300 for example. We can also crush polymeric foils. Here we have to use a cryo mill, because then we freeze it to very low temperatures and we embrittle the material, so we can pulverize it. we can crush metal foils. Just a short remark, foils is possible as soon as we are talking about massive metal pieces. It's not longer possible. But here we see with MM500 control, we achieved to crush metal foil. And of course, the black mass for the analysis to see the elements, XRF analysis, you can you generally normally crush it with the mixer mill, for example, the MM400 model. But in the recycling process, our mills are also used in terms of development of a process. So you have a small scale recycling production process. So the crushing step is performed with a SM300 cutting mill. So you see in the picture that we crushed the battery materials to a final fineness of 4 millimeters with a parallel section rotor and a sieve at 1500 RPM. So imagine there's a knife rotating or the cutting blade rotating, and as soon as the pieces of material are smaller than the sieve size, it passes the sieves and fall in the receptacle. So here we have a small scale shredding process. And last but not least, the sieving machines are used to separate the black mass from the shredded material. So the vibration and the sieves are used for fragmentation. Okay, so thank you very much for your attention. Let's have a look at the questions. Okay, perfect. So there were many questions coming in. One important question was, can you please explain again the difference between the planetary ball mills and the mixer mills? Sound is working? Okay, perfect. The main difference is the movement. So as you have seen, there's a different movement, and this also causes that the balls inside the jar are moving different. So generally speaking, you can say that in a mixer mill, you have this horizontal movement. You have like a shaking process. You have a lot of impact situations. So the balls are hitting the wall and the material. So we have crushing effects here. And this also leads to another energy conversion. So you're using the energy for crushing and for particle size reduction, and not so much for heat development. So if we compare a similar setup in planetary ball mill and mixer mill, the mixer mill is generally speaking cooler. So heat development is less. But you have to consider that this always depends on the application. So how many balls do you have inside the jar? Which is the velocity or the speed that you are running? So of course you can also have less impact effects when you just use a very slow frequency, which I can use for another question. There was someone asking how can you use ball mill for mixing? So of course you can use the mill without balls at all, and you just put in your material and you start mixing it at high frequency. So you have a very good mixture and a homogeneous result. But you can also use balls, for example, very light balls or very few balls, and then you just mix or process your material with low frequency, with low energy input, because you don't want to crush the material, you only want to mix it. So this is the possibility for mixing. What else comparing planetary ball mill and mixer mill? A planetary ball mill has bigger jars, for example, up to 500 milliliters, whereas the mixer mills have a maximum jar volume of 125 milliliters. So if you need a high sample amount, this is only possible with up to 125 milliliters in mixer mills. And In contrast, we have this easy handling at the mixer mill. So I prepared myself and I brought a jar. So let's see, can you see it? Okay, so this is a jar from a mixer mill MM500, and you just have the lid which you put on top and you fix it with these two screws. So for example, if you want to check your result during the process time, you can leave the jar clamped in the machine and you just lift the lid and you can have a look inside. This is very suitable for wet grinding processes, for example. Yeah, and then you can proceed with your process. I also have another jar, and here you can see the different kind of materials. So we have, for example, zirconium oxide, and this is steel. So two different materials, which is very important to avoid cross-contamination. Which leads me to a third question. Cross-contamination is important if you prepare your sample for in terms of analysis. So if you want to analyze your material, I think this question was coming from the recycling section. So you want to avoid, for example, abrasion of heavy metals. You have to use a material which does not really bring in material that you want to analyze. So for sample preparation, the cross-contamination is a very important point, and you can use different accessories with different materials. And what else is to consider for sample preparation? So many of you were asking specific questions. How fine do I have to grind? So this always depends on your analysis method. So some methods do have an idea about how fine the particles have to be prepared. But usually you have to grind as fine as necessary that your amount that you are analyzing is really representative. So that the mixture that you analyze has the same properties as your material that you have received, the sample as received. So fineness is one point, but remember, if you grind as fine as possible, you have other problems. So it's not always good to say, okay, I will grind as fine as possible. That will take longer than necessary. You have more abrasion, and also many samples are physically changed when you grind them in terms of, for example, heat development makes the material heating up, so temperature increases, and sometimes the temperature is also difficult for a material because volatile substances are not there anymore. You change the chemical properties. So there are many many parameters you have to consider, and as fine as possible is not always a good solution. There are some more questions. Maybe one last question before we start with the next session. Small cavities, that was coming from the mechanochemistry. We have small cavities. We now have 25 milliliter jars, or multi-cavity jars with 25 milliliters, or also 2 milliliter cavities. So there are many possibilities for proceeding small amount of materials, because I know that these are quite expensive, for example, in research of battery materials. So yes, we have small cavities. Okay, so all the other questions we will answer in the chat. Let's have a look at the agenda, what's coming next. So in the following, we will listen to the contribution of the other brands of Werder Scientific and discuss the particle and pore size characterization with Microtrack, the solutions for elemental analysis with ELTRA, metallographic preparation with QATM, and ovens and furnaces applications with CARBOLITE. So the next presentation will be from Jürgen. We already know him from the introduction. He's the Director of Product Management at Microtrack, and he will talk about the particle and pore size characterization of battery materials. Jürgen, we are very much looking forward to hear your presentation.
Yeah, Lena, thank you for the nice introduction. I'm going to show you now the particle process characterization techniques for your battery materials we can offer from Microtrack MRB. Microtrack MRB is also a unit of different business units, like the site in York, USA. They produce all kind of particle size analyzers like laser diffraction, dynamic light scattering, or the site here in Hahn. We are producing here the image analyzers for particle size and shape. And in Japan, we do have all the company Bell producing the Bell-Sorb equipment. And also here in Hahn, we are responsible for kind of porosimetry and pignometry equipment. I will start with particle size analyzers combining laser diffraction and dynamic image analysis. This gives a new dimension in particle characterization. We are combining these two techniques in our sync instrument. We can measure in the wet and in dry dispersion. And I give you here an example of an overview of the data acquisition. And you can see here various lasers, up to 3 lasers we do have. One is laser red, another one can be red or blue, and the third one even red and blue. Then we do have 2 detectors, one and 2. And in addition, we do have here the camera with a strobe light for the image analysis. The example where we use this for battery materials is shown here. Is a synthetic graphite. And what you see in the first picture is the particle size measurement only with laser diffraction. But there are certain particles of oversize. So the laser diffraction gives us a value of about 10 microns. But there are particles of 130, 60. So all these particles are shown here. Statistically, you will not be able to measure these with a laser diffraction. But in image analysis, we can follow these. And when we do this, and we get the combined information of laser diffraction dynamic image analysis showing us the oversize. This may have an impact also on the performance of a final electrode. You don't want to have these kind of oversized particles. Another example is milled coke. We do have, again, a particle size of about 10 microns, only with laser diffraction, and with help of the dynamic image analysis, we can detect even particles above the 100 microns, and you get a much better impression of knowledge of your material. The other techniques regarding dynamic image analysis we have in our ChemSizer series. The whole series can measure particle sizes of from 0.5 micrometers up to 135 millimeters, so it's a huge range. And typically, you see it here in the sketch. Particles are falling down, and a camera is detecting these. I will switch to the laser pointer. One moment. So particles are falling down here. A camera is detecting these images, and from these we can then do our particle size analysis. As an example, we show here four samples, 2 copper and 2 silver particles. The powder is either fine or coarse, and you see all the particle size, and here is shown the minimum dimension, the minimum width. There is not seen a real difference. Even when you compare all the sizes at D10, D50, or D90, either with a ChemSizer or even with a laser diffraction, for example, they are very similar. So we don't see much differences, but there are big differences, as we can see here in these pictures. So the silver particles are quite fringed, while the copper particles are spherical. And how can we check these? Well,
We can, for example, look for the aspect ratio, which is shown here in the first graph, or which is the ratio of the smallest diameter, xc min, divided by the largest ferrite diameter, for example. If this is almost 1, we have a spherical particle, and this is shown here for the copper, for example, and we are really about 1 with this aspect ratio, while for the fridge silver particles we get values around 0.6. Another value could be compactness, and even again there a value of about 1 is showing us that we are dealing here with spherical particles like this for copper, and values much less than 1 is showing us non-spherical particles, as we do have it here for silver. So with help of the image analysis and the shape factors, we can get much better information about our materials. So we were dealing with particles, so non-porous particle and a porous particle may have the same size and same shape, but they differ in their properties, like porosity. You may imagine that the porous particle gets a much higher surface area, then it may uptake moisture, catalytic properties may change in the processing, friction, and so on is also different compared to the non-porous particles. And how can we characterize porous materials, porous particles? One technique is, for example, a physisorption. Physisorption is a technique where we work at a constant temperature. That's why we call these kind of measurement curves isotherms. And in gas sorption, for example, with nitrogen or argon, we work at their condensation temperatures, which are quite cryogenic. So 77 Kelvin means 196 degrees Celsius. In the beginning, we start with vacuum. We evacuate the system at number 1. You see here the clean surface of our porous material. Then we start to introduce step by step our gas molecules, and these will fill micropores or lay around the surface. And we are here in the region 2, where we have monolayer formation, from where we can calculate surface areas or micropore filling. Later on, in the mesopores, we have a capillary condensation, so filling of pores with a liquid below saturation pressure. And at the end, we have filled all our pores and voids, and we can determine the maximum pore volume, for example. So we get at least 3 main informations. One is the specific surface area from this region and pore size. Now the example I will now I will show you the equipment. We have the BELSOB series for gas and vapor adsorption analyzers. This here is the largest instrument. You see here the BELSOB Max X. This can measure water vapor, gases, all kinds of other vapors. The Max G and the Mini X are determined or are dedicated to gas sorption. I will show you now an example we measured with the BELSOB Mini X on solid electrolytes. It's this lithium sulfur solid electrolyte, and this was produced either in a liquid phase or made in a solid phase and milled with using a ball mill, like from our friends from REG. You see already the coarse picture of this image scanning electron images here. Surface areas are 20 square meter per gram 3. And how did we get these? Well, there was a problem, because these samples must be protected against air. And how did we solve this? So, well, first we had a special sealing for our sample tubes, or you can also put the BELSOB Mini X, because it's very small. It measures only 28 centimeters in the width, 65 centimeters in the height, and roughly 47 centimeters in the depth. You can put it in a glove box. So the results are shown here. The isotherms of the ball milled lithium sulfur electrolyte shows a low uptake of gases, and that also results in the BET surface area of 3 square meter per gram, while the electrolyte we got from the liquid phase got a much higher surface area of about 20 square meters per gram. We also see that in that case we have to deal with some kind of pores in this lithium sulfur solid electrolyte from the liquid phase. In case you want to measure the density, also under protection against air, you can use the Bell-Pigno-L instrument. And because we can disconnect the measurement part from the control unit, you can also easily put the upper measurement part in a glove box. Another technique we use in battery characterization, particularly for the electrode and separators characterization, is the mercury intrusion porosimetry. Therefore, we have our bell pore equipment. We have actually two main equipment. One is the bell pore LP. This is for the filling of our sample cells. We call them dilatometers with mercury. And for low pressure application up to 450 kilopascal for macropores. And then we do have the high pressure versions, MP and HP. They can go up to 440 megapascal. So this kind of equipment is used for pore size and pore volume determination. The pore sizes we can cover is between 3.6 nanometer and up to the 1 millimeter, and can be measured very precisely and fast in about 45 minutes. For quality control, it can be even much faster. So we can measure up to 20,000 data points per instrument. There's no gas necessary, no liquid nitrogen. It simply works out of the box. How is the principle of mercury intrusion porosimetry? Mercury is usually a non-wetting liquid, and we need pressure to press it into pores. So the pressure we apply is reversible to the pore size. We can calculate this with the Washburn equation here. And the amount of mercury which goes into the pore is giving a number or value for the pore volume. So finally, we get pore volume and pore size with this technique. Some applications on electrodes. These were here non-calendared cathodes and anodes. And this example shows here similar pore sizes of these anodes and cathodes, but you see here the pore size distribution, but a very different pore volume you can see here on the left-hand side, for example. Another example is that we do have different pore sizes of the anode of about 200 nanometers shown here, or cathode of about 500 nanometers. So this is easily to detect with the bell pore mercury intrusion porosimeters. We can also measure membranes or separators. Here is an example for a smooth membrane, the blue one, a pore diameter of about 10 microns, and in red, folded membrane, where we get a pore diameter of about 20 microns. Or we can also have multimodal distributions of pore sizes, like here for separators between 90, 50, and 0.1 micrometers. A second one is giving only 2, 15, and 0.07 micrometers. So with this technique, you can easily get information about the pore size and pore volume of your electrodes and separators. I will summarize now the applications, so the problems and our solutions for your battery materials optimization. First one was the graphite and carbons, the particle size distribution, in particular the oversized distribution. And we use the sync, sync equipment, which combines laser diffraction and dynamic image analysis. In the second problem, we were dealing with metal powders about shape, size, and fringing and smooth surfaces. In this case, we use a dynamic image analysis, and the instrument was the Microtrack MIB ChemSizer X2. The third problem were solid electrolytes, where we were investigating the specific surface area and pore size distribution, as well as the density, and we used therefore the gas adsorption device Belsop Mini X, and with a special feature for air protected measurements. You can also use for the density the bell picking L. For anodes, cathodes, and separators characterization, particularly the porosity and and pore volume, we use the mercury intrusion porosimeter, the Belpor HP and LP. And with this, I thank you for your attention, and I'm looking forward for your questions.
Okay, and there's another company, Formulation, which was just acquired shortly, and also part of Microtrack now. And they also have applications in battery technology.
Yes, Formulation we acquired last month, actually, so this is brand new. And so my colleagues as France, they told me they also in the battery business. They even will give on July 12th own webinar. But let's have a look on the short presentation. While we were focusing more on particle size character and porous characterization of more or less final produced electrodes, they are in the step before for the slurry and the coating.
Okay, so wet material.
Yeah, and in that case, they were interested in the particularly the monitoring of control of the film formation, depending on heat, time, and so on. They had their own equipment, the current scan instrument, and yeah, so this is indeed an additional important product for us. Now, for not only for the battery, but now as shown, even dedicated for the battery research, so that we even coming from the slurry down to the final electrodes and membrane separator materials characterization.
That's very interesting. Yeah, it completes the picture that we have. Now let's have a look at the questions. So there were some questions coming in with regard to the Microtrack applications. So one question was, and I think that's not the first time that you hear this question, but can you please explain how safe is mercury intrusion? You know, mercury is not a very easy material. So how do you handle this material?
Yeah, so mercury intrusion porosimetry is a safe technique. So, and we put in the ISO 15901-1, the standard for the mercury, international standard for mercury intrusion porosimetry, also an appendix where we wrote down all the points you have to take care for safe handling with mercury.
Okay.
So our instruments themselves, they are very safe. I mean, we have sealed all openings. The hot vacuum pump is separated from the mercury, for example. We don't need any liquid nitrogen stuff and so on. Anyway, these instruments can be put on the benchtop. There's no problem. But again, for all handling, cleaning, filling of the dilatometers, I have brought here some of these. You see, these are the sample holders, so people get also an idea of the size. When you clean and fill these, you should do this, of course, under fume mode.
Okay.
So the fume mode is always mandatory. So you need this for safe working.
Okay. I think that's very good for the customers. So the next question was regarding to the particle size characterization. So you were mentioning ChemSizer and Zinc, two of your devices. So both have the dynamic image analysis. But what is the difference?
Yeah, so the difference in the dynamic image analysis is an additional tool we put into the laser diffraction to get information about the particle shape.
Okay.
So statistically, it does not have the power like laser diffraction. You get much more particles, but the few particles you measure with the image analysis, which are out of the size range you want oversize, for example, you will not detect with the laser diffraction. due to the low numbers, but you can see them in the image analysis. While the CAMSIzer systems are working purely on dynamic image analysis, but typically on a larger scale, larger particles.
Okay.
So these you cannot determine with laser diffraction. They are too big, actually.
Okay, so it's like an additional measurement set up in the zinc, so that you are able to to also see the bigger particles.
Yeah.
Okay. To make the measurement range broader.
And also to get information you usually will lose with pure laser diffraction.
I'm just looking at the questions because there are some more questions coming in. Just a second. So we have the questions of yes, okay, porosity. So porous materials, we have different kind of porous materials in battery technology, and also let's say bulk materials that are porous, and others are more pulver that are porous. So you have even a bulk or a powder. So how can you analyze these different types of materials?
Well, for us, these are at least in the first step all porous materials. So if we do have a bulk material, or parts of electrodes, for example, so we treat them in the same way as we have a powder, but we do have maybe differences in this. I show you here. So we do for mercury intrusion porosimetry. So we do have here these sample cell. For bulk materials, you will have a straight capillary. Mercury will drop immediately on the sample. For powders, we have the opening is closed. We have two side openings, and mercury will drop slowly on the powder, not to disperse it too much. So, but at least since the pores we are dealing typically in the range of micrometers down to nanometers or less, we don't care too much about the size of the particles, so we can.
And the appearance. So you can measure both systems, but you adapt the handling. If you talk about porous, I mean pulverous materials or monoliths. Okay, and then there was also the question. You were mentioning that we have porosity in terms of micrometers, but also down to nanometers. So mercury porosimetry is for larger pore sizes. How do you measure the very small pore sizes of only a few nanometers?
Yeah, so mercury porosimetry goes down to 3.6 nanometer when we go with pressures up to 400 gigapascal. But all the smaller pores, like micro or ultra micro pores in the range less than 1 nanometer, we may have in activated carbons, for example, or zeolites also. These we measure with gas sorption. So in gas absorption, we do have, as you have seen, the isotherm, actually two regions for pore sizes. One is in the micropores, pores less than 1 nanometer, you have a pore filling, because the molecules are almost in the size of the pores. So in larger pores in the range of few nanometers up, we can measure technically about up to 300 nanometers. That's the case where you have capillary condensation. So you have a liquefaction of your gas below the saturation pressure due to the pore size. And so we may have different methods, theories to calculate then from these effective pore sizes. Some are known, like the BGH, Bertrand-Hallender, based on the Kelvin equation for mesoporous materials with the capillary condensation, or density functional theories, non-local density functional theories, grand canonical Monte Carlo. So there are, I guess, about 40 or so more of such models.
Well, so that sounds a little bit complicated. So we have this physical mechanism of monolayer and liquid filling of the pores, and the different models to analyze or to translate the physical mechanism to porosity or to the real pore sizes. Can you just shortly explain if the customer is maybe new in this topic or does not really know a lot about the physics and the models? how can he use the machine? How is the handling? What does he see? There's a software coming with the machine, and
yeah. So the handling of the machine is more or less straightforward. Of course, you may have also some settings, but you can do this with them. Depending on the material, if it's mesoporous, microporous, or has low surface areas. So there you will have maybe some different settings, but this is straightforward. So then you get the result, which is the isosom I have shown to you, this graph. And then we do have analysis software with all these models. Mostly the BET surface area model is used for this surface area determination, and then we may have the GCMC, NLDFT, or BGH models, T-plots. So these are also explained in the manuals, of course, and you are always welcome to ask us. We will support you. It will be a pleasure for us.
Perfect. So as soon as we selected a model, we get the result in terms of pore size distribution, and this is a single plot. And perfect.
And pore volume
and pore size. Right. Okay. Perfect. So very complicated measurement, but very good solutions from Microtracks. Maybe one last question. I think this is more a practical question. There was this idea of inline measurement. You know what I refer to, that you measure in a process, in a battery process, you have the possibility to include your device.
Yeah, so it is for all the kind of, let's say, gas sorption, microporous material, this is not possible.
Okay.
So, but for particle size analysis, particularly for larger particles, we do have at least what we call the ChemSizer online system.
Online, okay.
So this is a system where you have an automatic sampling. So if you have a conveyor, particles are coming down, and then you have a kind of sampling system, and the material will then be tested immediately with a ChemSizer, and the results will be given directly to a control center, and the people there can adjust their process for the production to be to optimize the particle size.
Or to find out if something is going wrong.
Yeah. So ChemSizer online is one of these.
That's equipment. ChemSizer online. So we have many more questions. I think there's a lot of detail that you want to know. So please further use the Q&A chat function. We will answer your questions. But now it's time to proceed in the agenda. So next, just a second. Yes, okay. So we see you stay in the chat, and we will have a look at the topics of today, because there are some new participants who just joined our webinar, and we just want to shortly review the topic of today. The Werder Scientific company includes 5 brands. This is namely CARBOLITE GERO with oven and furnaces for heat treatment, ELTRA for elemental analysis, QATM for metallography and hardness testing, RETCH with milling and sieving, and Microtrack for particle characterization. So our companies are helping to meet the challenge of battery technology with enhanced technical solutions. And as you can see on the next slide, we offer devices for every stage of the battery life cycle, from the basic materials, raw materials, and the development of components or component manufacturing, the assembly of batteries, and the recycling of batteries. So our next speech is provided from Dr. André Klostermeier. He is a product manager and application specialist at ELTRA. André, the word is yours.
Thanks, Lena, for this nice introduction. And my name is André Klostermeier. I am product manager at ELTRA, and I'm responsible for marketing materials and also for applications. So I'm proud to present you the results we have and just give a short introduction. What is ELTRA doing and which solution can we provide for your requests? So the structure of the webinar is like this. I will shortly introduce elemental analysis and ELTRA. Then I will give you some examples of oxygen and nitrogen analysis, especially the components silicon nitride. And then I will talk about carbon sulfur analysis. I will have a short summary, and then of course we can finish with these presentations with some questions. So what is ELTRA doing and where we are located? We are located in Hahn. We have been founded in 1981, and our product portfolio is a special kind of analyzers, which is called combustion or inert gas fusion analyzers. We are dealing with the analysis of carbon and sulfur, and as well as the analysis of oxygen, nitrogen, and hydrogen. And another product we have in our portfolio is TGA. These products usually are these elements or these parameters are usually not suitable for analysis with other, I would say, analytical techniques like optical emission spectrometry or sometimes muffle furnaces. So we are specialists in these kind of analyzers, and how to perform this kind of analysis for battery components and which application we can provide is described in detail in the following slides. What do we have? Today I will present you data about carbon sulfur analysis and oxygen and nitrogen analysis. And typically we can perform this kind of analysis for primary and secondary type of batteries. And we are not fixed on a special chemical matrix. We can do it for lithium, we can do it for manganese, we can also do it for lead. So this is not limited. We are limited for carbon and sulfur, oxygen and nitrogen, but the base which we can use for analysis is not limited in general. So it is this kind of analysis can be performed for many materials. Besides this quality control of batteries, we also have the possibility to support research, and this is a wide field where you maybe know the applications better than me, because we can analyze for carbon and sulfur nearly any component which is used in this kind of batteries. So I will just pick up one solution we have, and maybe you have other ideas, and then we can discuss it in the following. Yes, what is the difference of our What is the difference of our technique in comparison to other techniques? Maybe you know that elemental analysis or maybe carbon and sulfur analysis is also possible with optical emission spectrometry or maybe with XRF spectrometry. So the functional principle of OES is like this, that you, for example, put in a spark on a sample and then you promote an electrode. This electron is falling down on the lower level, and then you get a special light. And then in comparison to XRF, you not excite an outer electron, but you also excite an inner electron, and then you also get the kind of signal, but this is in the other range of energy. So in both cases, you get a spectrum for multiple elements, not only carbon and sulfur, but also, for example, elements like titanium, manganese, or whatever. And this is a typical multi-element analysis, but only focuses on the elemental analysis of a surface in both cases. OES and XRF only mean, in most cases, only a surface analysis. What ELTRA can do is we can go into the deep of a special material. We combust all the sample or disintegrate all the sample, and this means that we can make a whole analysis of the complete sample. Well, what does this mean in detail? On the left side, for example, you see a very macro photo of lead carbonate. This is one sample a customer sent to us. This sample was subjected to a carbon and sulfur analysis. And in this special case, this means we put the sample into a graphite crucible, put it into the analyzer, And after analysis, the sample was completely burned. This means that all the carbon and sulfur which was inside the sample was released and could be measured by these techniques. So in comparison to other techniques like XRF or OES, we always destroy the sample, and this has the advantage that we, for example, can always analyze the whole sample, but it has the disadvantage that the sample is destroyed. It cannot be used for further evaluations. Well, what does combustion analysis mean in general? What features can we provide, and what is the, I would say, performance of this kind of analyzers? For carbonate sulfur, this is more or less very easy because we are not fixed on special concentration range, because we can start from very low concentrations, approximately 1 ppm, up to 100% for carbonate sulfur. For oxygen and nitrogen, theoretically, we also can analyze 100%, but in practice, there's no matrix or no sample which has 100% of oxygen and nitrogen, which we can analyze. So typical examples for very high concentrations, for example, are aluminum oxide or other oxides. High concentrations of nitrogen, for example, means silicon nitride or boron nitride. At the highest hydrogen concentration, we are usually, I would say, measuring is a sample of titanium hydride, and this means a maximum of 4%. In practice, we can also go higher in every case, but it depends on the sample. What does not depend on the sample, and this is also a big thing or a big difference between optical emission spectrometry and combustion analysis, our results do not depend on the matrix. And this means that we are always free to analyze the sample as it is. It doesn't matter if it is lithium, manganese, or cobalt, or whatever. We are always disintegrating the sample by combustion, and this means for us, it doesn't matter which matrix the sample has. So we can calibrate with, for example, primary substances or maybe reference material, which is based on another matrix. We just combust the sample to 100%. And this means, for example, that we also combust your sample to 100%. And this gives you the safety and the reliability that your result is always true. And heterogeneous samples, it doesn't matter because everything is also burned. And the shape of the sample does also not matter because you can have a powder, you can have a granular sample. All these things are not important for a combustion analyzer because at the end, the sample is melted, is disintegrated, and you will get the result. In detail, this principle for every combustion analyzer is the same. It's the ELTRA principle, and of course, it's also the principle of other combustion analyzer. You have a sample, you have a kind of energy, and you burn the sample. This could mean an induction furnace, it could mean a resistance furnace, or it could also mean an electrode furnace. The sample melts, and the reaction products are carried with a carrier gas, and you have typical samples like CO2, typical reaction products like CO2, SO2, hydrogen, and nitrogen. And all these gases you release from the sample are transported to a detector, and then you are getting results. And what you are seeing on the right side is a typical result of an elemental analysis, because you see just nice peaks, maybe with different colors. And these peaks are representative for your measurement and for your sample. And this result, for example, does mean you have a quality control of your sample. Typical analysis is oxygen, nitrogen, and hydrogen, and typical carrier gases, for example, are helium and argon. Detectors are, for example, thermal conductivity cell, and of course also an infrared cell. One thing which is maybe important for your lab or for your lab manager in general, elemental analysis does mean that you follow different standards. For example, optical emission spectroscopy means that you follow a different standard, and XRF means that you follow a special standard. For combustion analysis and inert gas infusion analysis, of course, you follow different standards. The most important standard, for example, for oxygen, nitrogen, carbon, and sulfur analysis is the ASTM E1019. This is more or less a very common standard where, for example, the analysis of nickel is described and of steel is described. And for other samples, for example, like sulfur determination in steel or in iron, or for example, titanium, you will have a huge list of standards which are released and where all ELTRA analyzers are compliant to. And this is something you have to keep in mind when you have to follow a special standard in your lab. Then please ask us if our analyzers are compliant to the standard. Usually it is, but when you have to follow a different analytical technique, for example, optical emission or XRF, then of course we are not compliant. But when you have a list of typical standards, which mean combustion or inert gas fusion analyzers, all our analyzers are compliant to this kind of technique. Yes, here you have a list of typical elemental analysis combustion technique. As I mentioned before, you have an induction furnace, you have an electrode furnace, and you have a resistance furnace. And this should illustrate that we are always a specialist for a special application and for a special element. This means, for example, battery components which are based on, for example, lead or manganese. This is the one which is on the left side, means always an induction furnace. When you would like to analyze, for example, coal, coke, or maybe other organic samples which you utilize in your battery components, you have to utilize a resistance furnace. This is the one you see on the right side. And oxygen nitrogen analysis always means that you have to utilize an electrode furnace with a graphite crucible. So this should give you a rough idea, for example, why we are talking to you so much, and maybe ask which kind of metrics do you have, which kind of application would you like to support. We have a lot of experience in this kind of analysis, so when you would like to perform, when you would like to make an analysis before you purchase an analyzer, please ask us. It's no problem. Just send us a sample, and before sending the sample, we can give you some recommendations which details are important for a reliable analysis. Yes, these are the two analyzers we are talking about in the following later. It's the CSI and 1HP2. The analysis procedure of carbon and sulfur analysis is more or less easy. You just log in a sample, weigh the sample, put it in an upper furnace, place a graphite crucible on the electrode, start analysis, and then you have these typical reactions I discussed before. You're producing CO2, you're releasing hydrogen and nitrogen, then you have some detectors like TCD cell or ER cell, and then you have your results, which are more or less calculated by this software. The example I just present here today is the analysis of silicon nitride. I don't have a sample from a customer here, so I just started with a CRM, and this CRM has the advantage that you know how repeatable the results should be, because you have a certificate of the CRM, and then it's easy to evaluate if the analyzers is able to measure the sample as precise as wanted. And this silicon nitride sample, for example, was just taken from the bottle, and we applied a typical analysis power of 6,000 watt, and the analysis time is about 3.5 minutes for this kind of samples. On the left side, you see a sample. It's a fine disintegrated powder, but of course, it's also possible to process samples which are in solid shape or maybe have a different shape than a powder. And these are the typical results, which means you always get some curves. One curve means the oxygen signal, and this is the one which is here colored black. And then, of course, you also get a signal for the nitrogen. This is the one which is colored here red. And on the left side, you see a typical result table of multiple measurement. On the left side, you see some typical sample weights. Due to the very high nitrogen content, you have to reduce the typical sample amount, and here in this case it's about 12 milligrams up to 18 milligrams, and you get quite repeatable results for nitrogen and oxygen. And this means, for example, that you have an RSD for typical measurements, for example, for nitrogen 0.5%, and for oxygen it's 2.6%. Keep in mind that the oxygen content was not certified here. So for your sample, it could mean that the repeatable is even better, or maybe when it's a sample from a production, it could be even worse. But it just should illustrate that we can perform this measurement in a very, very stable way. When we are leaving the world of oxygen and nitrogen analysis, the analyzers more or less look pretty the same, but the working principle and the analysis is a little bit different. For carbon and sulfur, the procedure is like this, that you apply your sample to a ceramic crucible, and this ceramic crucible is, for example, something like here, like this singer, and then you put in the sample, you have to apply accelerator, then you put this accelerator and the crucible to the analyzer, press start in software, and then all the sample is combusted. And in this case, for carbon and sulfur analysis, you only have some 2 ER cells, one for carbon or maybe 2 for carbon, and one for sulfur or maybe 2 for sulfur. The peaks are looking more or less the same because you always have an, I would say, combustion step and a detection step. But of course, we have a different procedure which causes the peaks here. And typical results for this kind of, I have results of different samples, and these are customer samples. On the one you see on the left side, I have lead sulfate. This was from a customer sample, and I also have lead carbonate. And these are typical samples for lead-based batteries. When you have, for example, samples which are, I would say, based on lithium or maybe manganese, this is no problem for the analyzer because it also can be combusted and analyzed for carbon and sulfur. But due to the fact that we have this battery seminar, some customers sent us some samples previously and would like to know how good or how bad is the measurement of carbon and sulfur in this kind of samples. We tried this analysis and we are proud to present you because it's a more or less real life sample. And on the next slide, we have the results. For example, lead sulfate can be applied with a very high or relatively high sample weight of approximately 70 to 90 milligrams. And you see here, we have a low carbon content about 0.15, and we have a high sulfur content of about 5.78. And the deviation is about 7% for carbon and about 3.8% for sulfur. For the customer, this, I would say, result was acceptable. You can be even better when you have very, very pure samples, but this was a sample from production side, and for them, for the customer, all these results have been found as good. The other sample we analyzed, for example, was carbon, was lead carbonate. We also started with carbon sulfur analysis. We also used approximately sample weight of 70 milligrams up to 90 milligrams. Here we found a carbon concentration of 3.23 and a sulfur concentration of 1.15. Here you also have different colors for carbon and sulfur. The red one means the sulfur signal, the blue one means the carbon signal. And when I have a look at the heterogeneity of the sample, the results are more or less pretty good. And again, it depends on the homogeneity of the sample, how precise this measurement could be processed. And this is, I'm looking at the precision because the next sample looks more or less pretty worse, but this is something which is depending on the sample. And the customer was interested in a rough, I would say, overview analysis of slag. And slag always means it's a residue from production. These samples are very heterogeneous. And due to the fact that we have a lead slag, in further disintegration is maybe a little bit critical because this material can be toxic. And you see on the left side that you have a lot of, I would say, heterogeneous sample. This means that, for example, we have a lot of balls, we have a lot of inclusions. And when you keep this picture in mind, when you have a look at the analytical results on the next page, we also weight here samples about sample weights between 60 milligrams and 80 milligrams. And here you have a wide deviation of carbon and sulfur. For example, you're starting with 4.5% of carbon up to 16.5% of carbon. And on the right side, you see the sulfur results, which are widespreading from 7.7% of sulfur up to nearly 14% of sulfur. For me, it was a little bit strange to send these results to the customer, but for them, it was quite okay. It just should give you an overview analysis of this kind of samples and maybe give an idea what is the maximum content of the sample. And this shows, I would say, the whole strengths and weaks of elemental analysis, because you can analyze very, very precisely when you have a homogeneous sample, but you also can make a rough overview analysis when you have a heterogeneous sample. In both cases, the analysis procedure is the same and it's always very fast, which means, for example, carbon sulfur can be done within 1 minute, and oxygen and nitrogen, for example, can be done within 3 or 4 minutes. And it's possible for nearly every sample, but the repeatability of results strongly depends on all these other details which are important for analytical chemistry, which means how homogeneous is my sample and how representative is my sample. And this is unfortunately, I have to quit this lecture now, because we are all limited to approximately 20 minutes. And this means, what can a combustion analyzer do for you? It is always focused on the elemental analysis of carbon sulfur or maybe oxygen and nitrogen. But it's possible for this kind of elements, for example, from the low ppm range up to high percentage range. And when you have maybe toxic materials, it's possible. When you have materials which are heterogeneous, it's also possible. And it's easy to use, as you have seen in the slides before. Just maybe put this away, the sample, put it in the furnace, and then, for example, press a button, and then you always get results. And this is something which makes elemental analysis easy. But please consider, when you have the best, when you would like to have the best possible results, it's always important to have in mind that you need a good sample preparation, and that you need a heterogeneous sample. When you are unsure if your sample meets your requirement, and when you have no clear idea what is maybe the content in your sample and what would be a good procedure, don't mind you, just contact ELTRA, send us a sample, and then you get a free of charge analysis. And then, for example, we can discuss further if it's good or if it's bad, or maybe when we can improve something. So, thanks for your attention, and hopefully I was not too fast, and thanks for your time. And when you have further questions, please ask them, and I'm happy to answer a lot of questions. Thank you. Kannst du irgendwie dann ableiten, wie viel Zeit wir haben?
Okay, so there's a question, and the question is it possible to analyze samples with high halogen content or with acidified samples?
Yes. In general, this combustion technique is suitable, I would say, for any matrix. But when you consider the chemical composition, you have to take into account that maybe some elements could disturb the measurement, or maybe could cause corrosions or some strange effects in the analyzer. And this effect could be suppressed by the utilization of the halogen trap. So when you think of analysis of acidified samples, or maybe of samples with high halogen content, please ask us and consider that you maybe have to utilize a special filter chemical. And this means, for example, you have to purchase a halogen trap, and then you are safe for analysis of every sample.
Okay, so there's a special solution for this application.
Yes, this is, for example, special solution for batteries, battery paste, or maybe, for example, some waste samples where you don't know what is inside, and you would be on the safe side for analysis. And this is a technical tool we can supply to you. And this is quite common in elemental analysis, because I would say other people are also have this trouble, for example, when they are analyzing salts, like, for example, sodium chloride or maybe potassium bromide. So these are common samples. And so we are, for example, we are very familiar with these kind of samples and provide a solution. And we are sure that this works also on long term, not only for, I would say, 5 samples, but also for 500 or even 5,000 samples.
Ah, perfect. Maybe just to add, in context of this question, there was also someone asking, is it possible to identify lithium with your method?
Yeah, yes and no. We have to distinguish between, I would say, what is the sample we combust, or what is the elements we measure. And we can only fix on elements we can measure for carbon, sulfur, or oxygen, nitrogen, and hydrogen. But the chemical element lithium would be interesting for analysis, but it has a, I would say, critical combustion behavior, and it's maybe critical to apply. But we have experience in other fast burning samples, for example, like magnesia. This is something we can do, but every sample is more or less welcome, and we can discuss it, for example, directly, and then we can say, what do we expect, what do you want, and then we can make some recommendations. So at the moment, we don't have any forbidden sample, but everything has its own, I would say, advantages and disadvantages as a sample. And this is something we can discuss, I would say, directly, because the world of elemental analysis there is very, very big.
Okay. Maybe you can just add, there was not or someone asking, or maybe also the general idea of your analysis method. Can you just shortly explain the difference to TGMS, because we also have gas and there are differences, and maybe you can just shortly explain what is the...
Yes, of course. Maybe we have a broad customer base here. Maybe everybody has a different experience in kind of analysis. And when you have, for example, other techniques like TGAMS, this usually means that you heat up your sample up to 1000 degree. And for example, when you are using this technique and you combust your sample and you measure CO2 or SO2, then, for example, everything is fine, and I would say the technique is comparable. But when you're going to other samples, for example, lithium or maybe ceramics or maybe lead or other samples, then you have to consider that we can apply a much higher temperature, for example, 2000 degree, 3000 degree. We can melt tungsten, we can melt ceramics. And this is for usually samples or techniques which are not accessible by TGAMS, because we have, I would say, much higher temperatures, and we can analyze and combust different samples. So this is the general technique. We don't measure thermogravimetric. We are measuring only carbon and sulfur, but we can focus on the combustion of the sample. And for this reason, we can apply a very, very high temperature, which is suitable for carbon sulfur measurement, or maybe oxygen, nitrogen, and hydrogen.
Okay. So it's an additional and more,
yes, it's a broader method, and of course it's an additional technique which you can apply when you don't need it, because you are not focused on this kind of elemental analysis. Everything is fine, and of course you don't need it. But when you have, I would say, special samples, for example, ceramics or maybe lithium metals, which are not suitable for TGAMS, then you can always ask if ELTRA can provide a technique which is suitable for your application. Sometimes I have to say, yes, it's possible, or sometimes I have to say it's possible, but in limitations, or maybe sometimes I have to say it's not possible. For example, liquid materials like mercury, for example, they cannot be combusted in an induction furnace analyzer. This is technically not possible, but the world of new materials is growing so fast that we cannot prepare, for example, I would say, application note for everything, and we have to discuss everything. But we have a broad experience, and sometimes in international lab we have very exotic samples, so we can give you recommendations more or less, I think, for every matrix. But sometimes this recommendation could mean, okay, it's possible, but it's not easy possible.
That sounds very good. Yes,
Thanks.
Thanks a lot. So there are some more questions. So you can stay in the chat function and answer these questions.
Yes, of course.
Okay, and we will proceed. Meanwhile, Andre is answering the remaining questions with the next, presentation. And this one is from QATM. We have already heard how rich mills are used for sample preparation and material development. Jürgen showed us how microtrack instruments are used for pore size and particle size characterization. Andre from ELTRA explained the fast and reliable elemental analysis of battery component materials. And now we are looking forward to hearing from two more Werder Scientific brands. This is QATM showing us the complete metallographic preparation of lithium-ion batteries, and CARBOLITE GERO talking about ovens and furnaces. So the next presentation comes from QATM and is presented from Parham Gemagami. He's a product manager, and Parham, please tell us how QATM devices are used to prepare lithium-ion batteries.
Thank you, Lena, for a nice introduction. Today, I want to introduce you the materialographic preparation of lithium-ion batteries from cutting to vibration polishing. In the table of contents, you can see at first I introduce myself, who am I, and after that a short overview we can see about the lithium-ion batteries, the structure of lithium-ion batteries, cathode and anode materials, and after that the manufacturing process of lithium-ion batteries. After that, I can introduce you the preparation methods, including cutting and mounting of the lithium-ion batteries, and at the end, the preparation method like grinding and polishing with the results of different parts of the lithium-ion batteries, like anodes, cathode foils, and cap and case. At the end, I want to thank my colleagues with acknowledgement, and you can also see the references that I used in this presentation. Who am I? My name is Parham Gemagami. I've done my bachelor in metallurgical engineering, my first master in the casting and solidification, and the second master in material science and simulation in the Ruhr University of Bochum. I've worked 6 years as a quality engineer in the bolt manufacturer and also as the process engineer in the turbine blade manufacturer. 18 months I've worked in the as a research assistant in the Department of Material Science in the Ruhr University of Bochum, and 1.5 years I worked in QATM as a materials engineer. And from 1st of May, I'm working as lab manager in Mamelson in QATM company. And also you can see some articles from me. I've worked on the different alloys, like the high entropy alloys, aluminium alloys, and also some rare elements like iridium. So a short overview over the lithium-ion batteries. 1972 company Sanyo introduced the lithium-ion batteries and used lithium in the anode. These batteries were the primary system. It means that they were not rechargeable. After that, in 1985, company Moly, as you can see here in the right image, they have used also the lithium in the anode, but in the secondary system. It means that batteries were rechargeable. But here we had the safety issue. It means that by lithium dendrites, we had the short circuit between the anode and cathode, and it could be very dangerous. After all, in 1991, company Sony used lithium in the cathode, and in the secondary system batteries, it means that we had the rechargeable batteries that lithium have used in the cathode. Then, in the lithium-ion batteries, we have the different type of batteries, like prismatic type, pouch type, coin type, and cylindrical. Today, I want to look at the cylindrical type. At the right image, we can see the structure of the batteries, how the arrange of the anodes, separator, and cathodes. And in the next image, as you can see, here we can see the charging process that the lithium ions go from the cathode to the anode, and discharging process that these ions coming back to the cathode. And all of them is through the separator. Now I want to make a comparison between the different cathode materials. For example, here we can see we have the lithium manganese oxide or lithium nickel manganese oxide. In these materials, we have a very good specific power, but the cost is not appropriate. It's very high. In the lithium nickel manganese cobalt oxides, we have a very good specific energy, good lifetime, low cost, but the charging is not so quick. In the lithium cobalt aluminum, the safety is very low. And at the end, the lithium iron phosphor oxides, we have in the most areas the best one. And this one is the newest technology in the lithium ion batteries. In the next slide, I want to show you the materials in the anodes. In anode, we can use the amorph carbon. We can use also the silicon alloys and also carbon silicon composites. What is the difference between the graphite and the amorph carbon? As you can see here in graphite, we have a structure and we have the constant in this structure. But in amorph carbon, we don't have these ones. A short introduction to the manufacturing process of the lithium-ion batteries. Here you can see it can be start from the slurry preparation, coating and drying, calendering, cutting electrodes, and here is the cell assembly. Here is the appropriate place to take the samples to check the quality and do the quality control. It's before the electrolyte filling, because after electrolyte filling, it's a danger to cut the samples, and also deep discharging make some changes into the structure of the lithium-ion batteries. Now I want to introduce you the preparation methods for lithium-ion batteries. Here you can see in the left image the cylindrical type lithium-ion batteries. Here you can see the cap and the case. If you want just to cut the cap and put out the jelly roll, you don't want to fill the battery. But when you want to cut the whole battery, you should fill it up. It means that you can use the epoxy resin, the cold mounting material like Chem 90 or Chem 92 to fill the battery, and you can put all the foils and separate the cathode and anodes together and then cut the whole battery together. In the first case, we can use the new machine of QATM QCut 200A and the rotational clamping tool. As you can see here, here is a rotational clamping tool. You can cut the cap of the battery from this part, and then you can put the jelly roll out of the lithium-ion battery. But if you want to cut the whole battery, or you have the bigger batteries, you can use the other machines from QATM, like here, QCut 350A. In this case, you can cut more than one slice at the once. It means that you clamp the sample here, and with this Z axis, you can also do the parallel cutting, and you can have more than one sample at one clamping. Here it means that it's better to fill the battery before the cutting. At the end, we have the cut samples. Here is the case of the battery. Here is the one half of the cap, the other half, and here we can see the anode and cathode foils. The best tool to cut the foils is surgical scalpel. It means that it should be sharp and you can cut it at once. Here you can see the effect of deep charging from the battery, because we use the normal batteries and we should deep discharging the batteries, and here you can see the gap between the coating and the copper foil and the anodes. And also in the cathodes you can have some cracks on the metal oxide particles. So For the mounting of the sample, we should use the cold mounting and epoxy resin. In QAPM, we have two products, Chem 90 and Chem 92, that you can use it. For example, for fixed the samples, for example, you can use Chem 50, is a UV cold mounting material, and you can fix the samples on the cold mounting molds. Or you can also use the cold mounting accessories. The cold mounting accessories is polystyrene, and they are impact resistant, and also they do not react with the epoxy resin. By most of the cold mounting accessories, they react with the epoxy resin, and you cannot use them. Also, you can mount more than one foil in one sample. It means that you can mount, for example, 5 or 10 foils from anode or from the cathode in one sample. Then, here is the mounted sample. You can see the cap of the battery with the case of the battery in one sample, and here you can see the anode samples and also cathode samples. Now, we can do directly an image from the stereo microscope that you can see the arrange of the anode, cathode, and the separator. But for the detailed investigation of each part of the lithium-ion battery, we should prepare them. It means that we should grind and polish them. Now, I want to introduce you the preparation method. It means that grinding and polishing of anode foils. In this case, we can start from the P600 with silicon carbide grind paper, and we can grind the anode foils to the P4000, and after that we can polish them to the 3 micron and 1 micron, each of them 5 minutes. For the grinding of the foils, we can use the adapter disc of QATM X-Tep. Is a Teflon foil that have the metal back, and with this metal back we have no flexibility and no elasticity during the grinding, and then we can have the flat surface. I've done these scanning electron microscope experiments on the Ruhr University of Bochum with help of my colleague, my last colleague, Dr. Alexander Kauska, and with the scanning electron microscope gel, as you can see here, JSM 7200. Because the mounting material of us was not electricity conductive, we should use the copper foil to make it electricity conductive. Here is a sample holder, copper foil, and also the sample. Now I can show you the results under optical microscope. As you can see here, here is the copper foil that has 2 sides coated and is coated by graphic coating. You can see here. Sometimes we have in anodes, we have the copper foil with 1 side coating. And here, under the scanning electron microscope, we can see the backscatter electron image and also the EDX map. In EDX map, you can see that the copper foil is shown by orange, and also we have the blue as graphite. Preparation method of cathode foils. You can see here for cathode foils, we use the silicon carbide grind paper from P600 to 1200, and then the polishing should be completely long. It means that 25 minutes for 3 micron, 40 minutes for 1 micron, and at the end is a half an hour for fine polishing with omega polishing cloth and Epoxyl F 0.1 micrometer. As you can see here also is the structure of gamma polishing cloth and omega polishing cloth. Why we use these long polishing steps? Because we have here the metal oxide particle. It means that they are the very hard particles that should be polished at the end. The results of the cathode under optical microscope can be seen in this image. In the left side, we have the lower magnification with the aluminum foil in the middle of the image and coated both sides. Here you can see the metal oxide particles, and in the higher magnification, you can see these oxide particles and also the aluminum foil. Here you can see the breakout. The breakout can be the artifact of the preparation method, but we cannot prevent it 100%. But the lower breakout, it means that your preparation method is better. And you can see also the polished particles here. The not appropriate preparation methods, after all, you can see many breakouts here and also non-polished particles. When we are going to the scanning electron microscope and under EDX detector, we can see the EDX map here. And in the middle of this image, you can see the aluminum foil, and the both sides is the oxide particles. Here, you can see between the oxide particles, we have the carbon as a suit, as you can see here in blue. And in the elemental map, you can see the aluminum, oxygen, and also nickel, cobalt, and manganese. It means that the oxide particle in this case can be the lithium, nickel, cobalt, manganese oxide particles. So now I want to introduce you the preparation method of cap and casing. It means in this case, we have the steel in the cap, and we can prepare it with silicon carbide grind paper from P320 to P1200. And at the end, we can polish them with Sigma polishing cloth for 4 minutes and just with Zeta polishing cloth for 2 minutes. The polishing has been done by Q-Pol 300 A1 Eco Plus. Here you can polish and grind the 6 samples at the same time. Under the stereo microscope, when you cut the sample like this and look at the surface in this direction, you can see the cap, case, and also insulating ring between the parts of the cap. When we are going to the optical microscope, at the end of the polishing, we can etch the sample with nitrile, which is nitric acid in alcohol, and here is 3%. We can see the coating and also the base material. As you can see here in the base material, we have the ferritic steel, and we have a coating on the surface of the material. We can also do the color etching with CLAM 1. The color etching product from QATM CLAM 1, you can do the color etching, and you can see here the grains of the base material very, very clear. Also, with the QATM software QPix Control 2, we can do also the coating thickness measurement. It means that when we have the etched sample, we can put the coating thickness measurement, and after all, we can see the thickness here. Also, for the color etching, we can do the thickness measurement. And after all, you can see here, we have the very accurate amount for the thickness in both cases. It means that the normal etching or color etching has no difference in this case. Here we can see the result under scanning electron microscope and also under the EDX detector. As before I have said, we have here the base material and the coating on the material. With the EDX point analysis, we can figure out that we have the nickel phosphor coating on the base material. And as you can see here, we can do the point analysis, and also we can do the EDX analysis on the complete region. And we can see here is the iron-based material steel, and we have the nickel phosphor coating on it. So if we want to do the EBSD and the cap in the case of the lithium-ion batteries, at the end of the polishing, we should do the vibration polishing. QATM has the Q-Pol Vibro that is designed for the vibration polishing of the samples. Here, we have used the Omega polishing cloth, the Epoxyl F 0.1 micrometer fine polishing suspension, also with the frequency of 80 with the 70% of the power, and also for 2 hours. Now we can see the results under scanning electron microscope and EBSD detector. At first, we have do the phase analysis, and we can see that here in the cap of the battery, we have 100% iron BCC structure. Also with EBSD, we can do the texture analysis. It means that we can do the inverse pole figures in different axes, in X, Y, and Z axis. And as we can see here in the Y axis, we have the preferred structure. It means that most of the grains has the direction of 1, 1, 1. And as you can see here is a preferred direction of the grains in the inverse pole figure in the Y-axis. At the end, we have done the hardness testing on the cap of the battery and also for the case of the battery. We have done this with QNES 60A+ Evo. As you can see here, here is the hardness testing indentations. And also at the end, you can see here a nice report that can be done by the QPix Control 2. And also we can do the hardness testing on the cap and the casing of the battery. Here, the average hardness of the cap is 117 Richters, and the average hardness of the case is 211 Richters. Here also you can see an overview from the report of the after doing the hardness testing. At this point, I want to thank my colleagues in the laboratory in Mamelsen and also in the product management. And at the end, I want to thank our cell manager, Frank Bleka, and the manager of product management, Peter Zimo, for their help in this project. Here you can find the references that I've used for this presentation. And also, I want to thank you for your attention. I'm pleased to answer to your question now.
Okay, Paham, I think these were very nice slides and very nice solutions to prepare battery samples. And also very good and great that you also added the analysis afterwards. So not only polishing and preparing the samples, but also how to analyze it afterwards.
Yeah, because these are the results that we can achieve with this preparation method.
Yeah. Mm-hmm. So there was good feedback for this, and there were also some questions. So we already answered questions in the chat, but can you please state why is it necessary to use longer polishing time when you prepare a cathode foil compared to an anode foil?
Yeah. In cathode, we have the aluminum foil and we have also metal oxide particles. It means that we have the ceramic particles. And in ceramic particles, the preparation for ceramic particles, it's known that we need the long polishing time. And because of that, we should do the longer polishing time to have a very polished particles in the cathode. But in anode, we have the copper and we have the graphite particles. And because of that, we don't need a very long polishing time.
Okay. And why were the harder polishing cloths used to polish the foils?
Because in the harder polishing cloths, like gamma polishing cloths or something like this, we use it because of the rounding. When we use the soft polishing cloths, then we have some rounding on the coating. For example, when we have the aluminum foil and we have the coating like these metal oxide particles, then we use the soft polishing cloth, we have the rounding on the coating.
Okay.
Because of that, we should use the harder polishing cloth.
Okay, and then you will see with this rounding, you will see in the analysis, you will see an artifact.
Yeah, we
Okay.
can see that. For example, at one side of the foil or one side of the coating, we have a very sharp rounding, and then it's an artifact of preparation.
Okay, oh, that's a good tip. And then there's a very specific question. So you have these different methods of polishing, and you have the vibration polishing. And when do you use, instead of vibration, the electrolytic polishing?
Good question. The electrolytic polishing is not always a good preparation method to prepare the samples for EBSD, because in EBSD we need a very low deformation. In electrolytic polishing we have also the very good, very low deformation, but it's when we have two phases, Then this electrolytic polishing or etching, we have a different surfaces in different phases. Then in EBSD, we cannot have the best results. And the best result we can achieve with electrolytic polishing when we have one phase and when we have non-ferrous material.
Okay, okay, that's interesting. So yes, you have to consider this. And then we have the feedback from the customers. I think it's not always easy to prepare samples because there are some breaking, or they say like sample coming out. Maybe have you the same experience? So what is happening here?
It's a very known artifact for metallographic preparation of cathodes. In cathodes, we have the breaking out. I also showed in my presentation that we had also, but we can also do prepare the sample that we have the low number of this breaking. When we have the many breaking outs and unpolished particles, then we cannot analyze the result very well. But a very low number of breaking out, we cannot prevent it. But it's we want to do it as we have the lowest number of the breaking outs.
Okay. Do you notice that immediately, or can you?
Yeah, you can see it as a hole or as a pore in your coating in the cathode, for example.
Okay, which is not coming from the sample.
No, it's coming from the preparation, most of them.
Okay. So I think there are some more very specific questions. So nice to have you here. I hope that you will stay and answer the questions in the chat.
Absolutely, I will stay here, and you can also, all of you can ask your questions in the chat. I will answer them.
Very good. Thank you very much.
You're welcome.
And now let's have a look. There's one presentation left, and this one is coming from CARBOLITE GERO. So CARBOLITE GERO is one of the 5 brands of Röller Scientific. And for the participants who just joined our webinar, I would shortly give an overview of the organizational structure of Röller Scientific. So Röller Scientific covers different technologies with its 5 manufacturing companies. These are namely CARBOLITE GERO for heat treatment, ELTRA for elemental analysis, QATM for metallography and hardness testing, RED for milling and sieving, and Microtrack for particle characterization. So as you can see in the next slide, this is an overview that shows with our different technologies, we offer solutions for every stage of the life cycle of a battery. And for the next talk, we will move to England, to the beautiful town of Hope. This is where the CARBOLITE GERO's Director of Sales, Tom Gold, and the Head of Marketing and Product Management, Fabian Uhlemann-Kölli, is sitting.
Thank you, Lena, and welcome to today's presentation. For those of you that don't know, CARBOLITE GERO manufacture ovens and furnaces from ambient to 3000 degrees centigrade. We have 4 different categories of systems, starting with ovens that run up to 700 degrees centigrade. Then we have hot wall furnace systems that operate at 1800 degrees, as well as our tube furnace solutions that also run up to 1800 degrees centigrade. And then we have our vacuum furnace solutions that operate up to 3000 degrees centigrade. We also have a range of special applications and custom designed products. So most of you will know this anyway, but we'll start by looking at what makes a good battery. So to start with, a homogeneous sample. So we need a pure material, and that will create a longer lasting cell and also a more efficient power source. It needs to be pure and lightweight, which will allow more efficiency. We need to ensure that we've got a very good crystal structure. So the crystal structure is important to ensure that the ions pass effectively between the anode and the cathode layers. The electrolyte, so ensuring the right electrolyte is being used. This will increase the energy density and the overall capacity of the battery. And then finally, not to undervalue this, but safe materials. So using the wrong material type can present a potential safety risk. So just as an example, if you take pure lithium, that will burn freely in air. So making sure that you get the material choice correct is extremely important.
Yeah, thanks a lot for that, Tom. Furthermore, we have many steps and applications to manufacture the raw materials for a new battery. And thereof, we have mainly graphitization, debinding, calcination, drying, and also machine learning. So this is very important that those materials are further developed so that the battery cells are protected from corrosion and hence their electrical performance, and especially inhibit the dendrite growth, which are very long needles, which may destroy a membrane or the cell material itself. And therefore, the machine learning is a very important, not last step, but nowadays it's the first step, so that in very huge and large databases, those informations are stored, and when you want to develop new materials, they can be searched and further used to develop new materials. So the battery materials, they consist usually of a casing, the cathode, the anode material, the electrolyte. There are some collector foils for the cathode and the anode, a separator, and the additives. Usually materials are steel, aluminum, the LCO, NMC materials, which are usually lithium carbon oxide or nickel manganese oxide, certain lithium salts. Well, in general, lots of aluminum, copper, and polymers are used. And on the right-hand side of the table, you can see its percentage, which is usually common and used in those battery materials.
Okay, so we're going to start by looking at the synthesis of graphite. So in this case, we've assumed that we are starting with a carbonaceous start material. So some of the weight has actually been removed already from the material. If you do want a bit more information about the whole graphitization process, so from the raw material through to the final composition, then please get in touch via the Q&A feature.
Yeah, talking about the graphitization process, it starts usually with the debinding, then with the carbonization, and then with the graphitization step. The graphitization step itself is very important to achieve the layer arrangement. And as you can see in the diagram on the right-hand side, it is a reordering of the tetrahedral structure to a plane structure. So there is an aromatization happening so that the layers are moving closer together. It's usually about 3.4 angstrom. This happens at about 2000 degrees Celsius and also depends on the precursor molecules. So that when the layers are moving together, they are stacking to each other with van der Waals forces. And yeah, this is mainly the effect which is very important for the graphite materials, so that the positive lithium, in this case, ions can be moved freely through the arrangement, so through the, or what is it, through the gaps of the graphite material. Yeah, just showing an overview about the 3 steps which we have discussed before. Graphitization, the last step, above about 2000 degrees Celsius. Before you can see a carbonization step, and at the very beginning there is the pyrolysis or the binding step. Usually it is to release small molecules so that the carbon atoms can connect to each other, and it starts usually with some aliphatic compounds which are released, even some aromatic compounds, carbon dioxide, methane, so very small alkanes. And at higher temperatures, which happens above 1000 degrees Celsius, also hydrogen is released and some CN structure or small CN molecules. Those volatiles, they cannot just be released to the environment, especially when you think of an industrial process. It would be a high amount of environmental hazardous materials, so they should be converted with an afterburner, for example, into, let's say, non-poisonous and non-toxic gases. It would be mainly water. Well, some CO2 will be also there, but this is not as dramatic as methane in this case.
Okay, so furnace systems that are used to achieve this. For the main weight removal, the hot wall systems are really bearing the heavier workload. So if you look on the left-hand side of the screen there, we've got a small tube furnace, and this would typically be used for grassroots research. So we're thinking small loads of around 100 mil up to 20 litres. But the thing to bear in mind with something like this is that we don't have a heated gas outlet and we don't have an afterburner system. So understanding the process and managing that risk sits with the operator and the process owner. Then for bigger systems, we've got furnaces like the GLO, which are pictured in the middle here, and a smaller version on the right-hand side. And these are good up to temperatures of around 1300 degrees. So the GLO's especially been developed in this format to cope with the off gases that Fabian's just highlighted. So we've got a full safety system, we've got purge tanks, we've got an afterburner and a trace heating line on the exhaust to ensure that we've got a very safe process. Just stepping back to the to the tube furnaces again, bear in mind one other benefit of the tube furnace is that you can operate up to 1800 degrees. So we're getting closer to those top temperatures that Fabian's just highlighted. Okay, and then for graphitization, these really are precision instruments by comparison to the GLO and the tube furnaces we've just shown you. As I say, those products are doing the dirtier work. But for graphitization, we need cold wall furnaces, and these are lined with a graphite felt insulation. The heating system sits inside the containment. So whereas before we've got a heated system on the outside and the containment inside for the off gases, now everything is inside the outer containment. We use, again, we've got an afterburner system on the side of this module here, and the purge tank for safety. To measure the temperature, we're using a combination of thermocouples, so physical thermocouples and optical pyrometers. The systems that we manufacture actually utilize both to give us a very well-controlled thermal cycle. We have manual and semi-automatic and automatic versions of the systems that you're seeing here. And we do have a white paper which includes some XRD analysis of process material. So again, if you have any interest in that information, then please get in touch via the Q&A. So then moving on to this, we're going to look at some other materials and processes that are important for production of battery materials.
Coming to another very important lithium battery and solid state battery material, which is nickel. It plays a key role in the development because the density of the battery materials increases a lot. That's why it's also very important and interesting to have a look to the process, how to get and chain the nickel. So the nickel is usually raised by a so-called flotation process. So you put some chemicals into a very big pot, and you can collect the nickel raw and ore material from a surface. This you put into a roasting process to get a kind of copper iron nickel roasting with air. So the oxides are then but these materials are converted into oxide salts. Those salts are then melted together with sodium sulfide. So this is a separation process that the copper and the iron is separated from the nickel so that the nickel sulfide remains. This nickel sulfide is then oxidized with air into nickel oxide and reduced afterwards with coke. So a lot of coke is put into this process to get and receive a nickel with a, let's say, purity, which is okay. And the raw nickel is then electrochemically purified to about 99% approx, and to reach an even more pure nickel, which is very important. What we learned at the first slide from Tom, he said we need very, very pure materials for a long, long lifetime of the materials. It is then received via the Mond process.
Okay, so in this example, we have a seesaw furnace arrangement where the process cycles between two process steps. So that's the roasting and the calcination. So the nickel sulfide is oxidized with air in the calcination phase to give us nickel oxide and sulfur dioxide. In the reduction phase, the nickel oxide is reduced with the coke to raw nickel. And as a batch system, the TSO, which is the furnace you see on the left-hand side of the screen now, would allow the material to be mixed. So this ensures a very good gas absorption into the material, which encourages the reactions to take place. For continuous operation, we also have TSR systems. So this allows you to feed material in at one end of the furnace and collect it at the other. So we're going from sort of a batch lab scale process to more of a pilot plant or even a production furnace system on the right hand side. So we've got a short video for you now. It's just a quick look at our rotating tube furnace. So you can see the inclination of the tube actually encourages the material to flow through the system, and that will dictate the speed in which it flows through the system as well. We can control the gas types, so we can work under a combination of inert gas. The rotation speed of the tube itself is also very important in controlling how quickly the material moves through the furnace, and therefore how much heat it sees, what the residency time, as we refer to it, would be of the material. We can split the furnace into several temperature zones as well, and that's important depending on the process, the reaction that you're trying to encourage. And as I said, materials in this system can either be fed in batches or continuously. So we've got a variety of hopper solutions and feed assemblies. These are, I'd say, one of the products where running a trial is quite important, because the material characteristics behave slightly differently when they're heated up, the flow characteristics. So if you do have an application, if you get in touch with us, we could look at setting a trial up and processing some material for you.
Yeah, in a lab scale, the last process, the Mond process, is achieved via a so-called chemical vapor transport reaction. On one hand side of an ampule, you have the raw nickel, and on the other hand side, you have the pure nickel, which is transported with a gas. In this case, it is carbon monoxide. It is a molecule which connects and binds to the nickel, and then it brings the nickel into the gas phase, and in the hot zone it decomposes and crystals of nickel is grown. Well, this is just a very small and little lab process. In the industries it is done a little bit differently. There you have very, very large vertical tunnels with some catalysts in the end, and it's just flown from the bottom to the top, and the carbon monoxide just takes the nickel from that pure nickel 99.9% from the electrochemical process, and then it lifts upwards to some catalyst, so that you do not need the full 180 degrees Celsius. So at a little bit lower temperature, it decomposes, and it was then deposit in a different area, and it can then be physically removed.
Okay, so the CVT process is best handled in a multiple zone furnace. As Fabian just demonstrated, the material needs to see 2 different temperatures for the reaction to take place. So the gradient furnace, which is a modification to one of our standard tube furnace products, is the best product for that particular application. And as Fabian said, the raw nickel would sit on the left-hand side and the pure nickel sits on the right-hand side.
There are, as you might know already, many different materials developed and also already in use and in testing. And there is, especially in the silicon chemistry, it's very interesting that there are high densities achieved, so that a combination of lithium and silicon can increase the density and also the capacity by a factor of 5 to 6. As we know already, to have a great lithium transport, it is not just silicon, which is very interesting, also carbon, but in a different modification. Those are, for example, carbon nanotubes. The carbon nanotubes are arranged in a CNT scaffold, so that along the tubes the lithium can be directed exactly to the destination, which is the collector, so the current collector in this example. And many different anode materials are, let's say, optimized in that way that, for example, niobium tungsten oxides is added and used because it allows the lithium to move much faster. And that means here in this example is shown that there is a fast charging possibility for 320 kilometers within 6 minutes. So it's yeah, a very important thing to combine many different materials and to find its best usages, so that the materials and the batteries have a great chance to change our daily life. As you know, batteries used in mobile phones, cars, even in trains or in trucks. And there are many companies working on this topic, for example, the Wacker Chemistry, or that there is not just graphite as an anode material, but also other carbon similar materials. You can coat those materials to extend their lifetimes of the batteries, and also to have larger batteries with a lower density, so that it is lighter. And especially in car and automotive industries, you have a lighter battery to have a longer distance to drive. Here is an example of a GLO from us. This GLO furnace is used for a process to synthesize some lithium silicon material, for example. This is done in a GLO with quartz boats, and those huge quartz vessels or quartz boats, the material is placed in thin layers so that evenly the material is distributed with heat, so that the synthesis can be run without any interruption. As you might know and imagine, as the thicker those layers are, the longer the energy needs and the heat treatment takes to fully convert the material in the desired composites.
Okay, so for the Wacker project, we supplied a GLO system. So again, if you remember with our when we looked at our product types, this is a hot wall system, so it's doing a lot of the heavier lifting in the process. It's got a special gas system fitted to it for this application, and that allows the operators to run under a combination of air, hydrogen or nitrogen, and the torch safely burns off any of the gases again. So this means that we've got a safe operating system that's not emitting a lot of dangerous, hazardous off gases into the local environment. The system also operates with a fast cooling, so we can improve the process time, and has a maximum operating temperature of 1,100 degrees centigrade. So just to finish up on the GLO and the HTK, we've got a couple of technical articles here that are specifically linked to this industry, where the people that have written the articles have used our GLO and or our HTK. So if you're interested in seeing a real world application, then you are free to download these from the usual resources. And that brings our presentation today more or less to a close. I'd like to just highlight that we do have a global network, as Lena's mentioned before, that can support you with your applications. We've got solution centers that include the use of lab equipment, demo equipment, so we can run trials where that's possible. So we look forward to hearing more from you in the future. If you would like to stay in touch and sort of see how things are developing within the business and any new releases we've got coming up, feel free to scan the QR code you see on the screen there now, and that will link you to all the usual online media platforms that we utilize. And I believe, Lena, there've been a few questions during the course of the presentation, and I'm going to hand over to Fabian, who'll be able to answer them, hopefully. And once again, thank you for joining, and look forward to speaking to you soon. Bye-bye.
See you. Bye-bye.
Okay, Fabian, thanks very much. You will join us for the question and answer session live. So feel free to share your camera and your voice so we can discuss the questions from the chat. There were numerous questions. Some are already answered. The other one we will answer later. But maybe you can explain for all of us, are your furnaces able to handle any kind of pyrolysis gases?
Yeah, thank you for that question, Lena. So let's say it's a little bit tricky because there is no furnace which can do everything. So that means we need to carefully discuss about which off gases are they abrasive, corrosive, so that the retorts material and also the gas outlet, that they are safe, and that we also can safe handle the pyrolyzed gases. And there might be some scrapper washer systems, just to scrap some corrosive chlorides or bromides and other corrosive gases, and afterwards the organics can be converted into CO2 or let's say water, NOx gases, just by burning with an afterburner. And we just have to make sure that the materials suit those pyrolysis gases, and that we might not just use a standard stainless steel, but that there are special steels like Inconel 601 or even Inconel 625, and there are also Wasser Hastelloy steel alloys existing, which are very, very well suited and commonly used in industries when working with those materials and off gases.
Okay. And we also see that you showed us the application of thermal processing of recycled battery materials to extract the reusable materials. So maybe you can just state, are there specific challenges or specific solutions for this application of in the recycling? Because I think we all see that these applications or these let's say this section of the battery life cycle process gets more and more importance.
Yeah, there are usually multiple stages, though, between chemical, let's say collection of the materials, that we have some floating processes. The materials must be, or the batteries must be disassembled because they might be, it is, let's say, not a security case, but it might be very, very difficult just to crush them so that they do not explode. So they must be slowly disassembled and later on crushed. Then they must be heated and maybe, let's say, ashed and burned with some rotary tube furnaces so that we can get rid of the membranes and some other electrolyte materials to retain some rare earth materials. I talked in that presentation about niobium, which is also a raw material. So to gather and retain those materials, there is a long process chain. You might know that already. And after ashing and heat treatment, there are furnaces called cupellation furnaces, so that there is an additional lead oxide which you add, and this will react with many salts, so oxide salts, to retain the pure metal at the end, so that you can reuse those materials in the future. But it is all still under research. I think the heat treatment and the recycling of the battery materials, it's still very, very, I don't want to call it unknown, but there is lots of R&D still going on to get in a cheap and easy process running.
Right. There are so many different ideas of what is the best recycling route for which kind of battery. So we have to be very versatile, and as you shown, you have many solutions to find the right one for each application. Yes.
Yeah,
Very
especially in R&D, as you said. So if we can help with the R&D case and with the furnaces, we will help you. I would not say that we would like to manufacture large-scale industrial furnaces, because this is not our main focus.
Okay, yeah, and this is also another idea and another question from the chat. You talked about the R&D or the small scale applications. So another very important topic at the moment is the solution of solid state batteries. So do you have any experience with this kind of material?
Yeah, so we are not the people who are providing and let's say who are helping with the assembly of solid state batteries, but we help with the chemical synthesis. So everything which belongs to sintering and to select the right furnace, so starting from drying the materials to the debinding and also pyrolysis and then the sintering, we can offer a very, very wide range, and it really doesn't matter if you have to heat treat under air, or if you have to heat treat under an inert gas or even hydrogen. This is really nothing new for us. As you know, we have experience more than 85 years, and therefore we made many different furnaces for the synthesis of salts, and especially for solid state batteries, the materials. Yeah.
Okay, that's interesting. Of course, the inert gas atmosphere is very important for these kind of materials. Perfect. So there are more questions in the chat. I think you can answer them. Yes, I think in the next minutes.
Yeah, I will.
All the questions we have not answered in the chat or the question and answer chat function, we will answer them by email after the webinar. Thank you very much, Fabian, for joining us.
Thank you, Lena.
Here. Yes, and see you soon.
See you. Bye-bye.
Goodbye. Yes, and for all our attendees, thank you very much for attending the Werder Scientific Webinar Day. So I hope that you will take home the message that Werder Scientific provides a multidisciplinary approach. So this distinguishes us from other companies who focus on one single process step in the battery life cycle. We hope that you enjoyed and that you gained valuable information for your daily work. You will receive a follow-up email by end of this week. There we will provide the presentation slides and also a screencast of the webinar. So thanks again for attending, and we hope to see you soon. Goodbye.